Chapter 12, The Science of Electronics DC-AC. Complex quantities. The Cartesian coordinate system is a way to indicate the location of a point on a plane or in space. For example, the point x equals 5, y equals 6. You go over 5 on the x, up 6, and there's the point. However, for the Cartesian plane system, the y-axis is symboled with j, plus or minus j, so you're up j6. In AC work, it is useful to visualize AC by drawing a phasor. A phasor is a rotating vector that used to describe an AC quantity. It is represented by a line drawn from the origin to a point. So if I was to draw that vector, I would just start at the origin, which is the 0, 0, and go up. And the phasor rotates counterclockwise, and that would generate a sine wave. Two notations for complex numbers are rectangular and polar. Both show a vector or phasor reference to the origin. For example, the same points that we used before, we can, instead of just going 5 comma j6, in rectangular form it would be 5 plus j6, which means you just go over 5 and up 6, and you're still at that same point, but now it's a phasor because of the plus sign. And it can also be expressed as 7.8 at an angle of 50.2. And to get that 7.8, you square the 5, square the 6, take the square root of it. That'll give you 7.8. And the angle is found by taking the inverse tangent of 6 over 5. And the inverse tangent on your calculator is the second function. By dropping by dropping a straight line from the end of the phasor to the x-axis, a right triangle is formed, which can be used to show the relationships in AC circuits. So here's that angle. This right here is your x value. This is your y value. So basically what you're finding is the length of this phasor, and that in terms is the Pythagorean's theorem. So it's x squared plus y squared square root will give you the length. And again, the angle, theta, is tangent, inverse tangent of opposite over adjacent side. Basic trig functions as well as Pythagorean theorem allow you to calculate parameters for right triangles. So on the same lines as I was just talking about, sine is opposite over the hypotenuse. So here's our angle. The opposite side is that one. Hypotenuse is opposite the right angle. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And this is the same relationship that I was talking about before. The impedance, the 90-degree phase shifts that occur naturally in reactive circuits affect the opposition to AC. The total opposition in a complex quantity is called impedance. So it's no longer resistance. We have to symbolize the total opposition because we have capacitors and inductors now in the circuit. We can call it impedance, and it represents the resistive and reactive components of a circuit. Resistance is plotted along the x-axis, capacitive reactance is plotted along the negative j, and inductive reactance is plotted along the positive j. So as you can see, inductive reactance, capacitive reactance, and there's your resistor. Impedance is the phasor or the vector sum of the resistance and the reactive powers. For a basic series RC circuit, the development of the impedance triangle is as follows. When you're looking at the resistance and the capacitive reactance, the impedance is the hypotenuse of that triangle that's formed. So basically your z is equal to square root of r squared plus x of c squared, and we're still at that same angle, inverse tangent of x of c over r. And for series circuits, this would give you the polar form. If you wanted to express it in the series term, you would use the rectangular form, and it would be r minus jxc. For a basic series RL circuit, the development of the impedance triangle is this way. It's basically the same formula. The only difference is it's plus j x sub l. So again, we're looking for the hypotenuse. So it's r squared plus x sub l squared, and the angle inverse tangent of x sub l over r. So for an inductor, this angle is positive. For a capacitor, it comes out to be negative. As an example, show the impedance triangle for the RC circuit. Here's the circuit. Now, before we can do anything, we've got to find the capacitive reactance, which is 1 over 2 pi Fc, which is this formula right here, 2 pi times 1k times 0.07 equals, then go 1 over x. So you've got 6.8k in series with a 3.3k ohm impedance. Square r, square x sub c, add them together, take the square root, you get 7.6, and then the phase angle, they didn't find the phase angle, but the phase angle would be found, which would be this angle right here, is the inverse tangent of x sub c divided by r, and it's negative. For the inductor, again, a series circuit, so it's r plus jxl, and L, our XL is 2 times pi times frequency times inductance. Frequency is 36K. Put the numbers in, you get 3.39. So here we end up with 7.6, and again, here's our angle theta, and that's equal to the inverse tangent of x sub L divided by R. Voltage phasors. In any series circuit, the voltage phasor diagram can be obtained by multiplying the impedance phasors by the current. For an RC circuit, this looks like, so basically you're just multiplying the current by each of these quantities, and that will give you VR, VS, and VC. The same relationship exists for RL circuits. Multiplying current times the ohmic values yields those voltages. Show the voltage phasors for the RC circuit. So here we've already found the total impedance from the previous example to be 7.6K. We find the current by 10 volts RMS divided by 7.6K. We get a current of 1.32 milliamps. Multiplying that 1.32 milliamps by 6.8K gives a resistor voltage of 8.98. 1.32 times 3.39 capacitor voltage. And then this is our total voltage, which is our source, which is 10. For a series RLC circuit, combine the reactive elements first, then calculate the total impedance as you did with the simple RC and RL circuits. A simplified example is XL is 2K, XC is 5K, R is 4K, and VS is 10. You combine XL and XC, so basically what you're doing is the total reactance is XL minus XC, or I probably should have wrote XC minus XL. So it's 5K minus the 2K, which gives us 3K. And if the, this isn't right, hold on. That doesn't make sense, erase that. So if XC is bigger, then the answer will be negative. If that's all right, hold on. I got that backwards too. I think I had it right the first time. Let's try that again. XT is XL minus XC. So if XC is bigger, that means the circuit's more capacitive because it comes out to a negative number. If XL is bigger, it comes out to a positive number, the circuit's more inductive. So here we take the 2K minus the 5K gives you 3K, and what they did here was they found Z as being R, so 4K squared plus the 3K squared, which will give 5K, and the series of this would really be R plus JXL minus JXC, or in it would be minus J3K, and you substitute the R because it's the capacitor's bigger, so it's the difference between the two of them. Impedance phasors. So here's the phasors where the resistance is on the X, L, and the C goes down. XL minus XC, that gives you the 3K. This is bigger, so the phase of the phasor is down. And here, there's your impedance. And with this, you can also calculate the current. Just divide it out by the total impedance. Voltage phasors. Multiply each impedance phasor by the current, and you'll get the resulting voltages. Series resonance is a special case for an RLC circuit where XL equals XC. So when you have XL equaling XC, they basically go to zero, so then all you're left with in the circuit is a resistive element, and the voltage across is equal to but an opposite of the phase. The frequency at which this takes place is given by the equation. So that there's a particular frequency, and you find it by just plugging in the inductor value and the capacitor value, taking the square root of it, multiply by 2 pi, press the equal sign, and then press your 1 over x key. Ideally, what is the resonant frequency of a circuit with a 360 picofarad capacitor and 270 microhenry coil? So again, plug in those numbers in. It would be 510 kilohertz. Series resonance circuits are characterized by an impedance minimum in the circuit or a current maximum at the resonant frequency. So they're just showing the graphs here, and this again is because the impedance at resonance is just equal to the resistance, and to either side of the resonant frequency, the inductive reactance and the capacitive reactance don't cancel each other out, so you end up having a higher impedance. And because we have the low impedance value at resonance, remember, the smaller the current, or the smaller the resistance, the larger the current. So we have a current maximum at that value. These characteristics make series resonance circuits useful in bandpass and notch filters, as well as any other frequency and selective circuits. Key terms. An imaginary number is a number plotted along the positive or negative y-axis. Imaginary numbers in electronics are shown with the letter J with them. A complex number is a number that is described by both a real and an imaginary term, or by showing a magnitude and direction of polar notation. Rectangular notation is a method of describing a complex number by giving the distance along the x-axis first, and then the real part followed by the distance along the y-axis, or the imaginary part. Polar notation, a method for describing a complex number by giving the magnitude first, followed by the angle with respect to the positive x-axis. Impedance is the opposition to AC. It is a complex quantity with both resistive and reactive components. The magnitude of impedance is abbreviated by Z. Resonant frequency is the frequency of an LC circuit where the magnitude of XL and XC are equal, and a bandpass filter is a circuit designed to pass frequencies around resonance and reject other frequencies.